Suppose that I have two inductors which are connected in series. So I have an inductance L1 and an inductance L2. And I would like to know what is the equivalent inductance of this network. So a little bit of intuition here, what you should think to yourself, so your little kind of thought bubble, is this is a coil of wire. So longer coil is more inductance. Right? That's our kind of think to ourselves, how does this system work? Coil of wire, so longer coil gives us more inductance. So inductors behave like resistors. So inductors combine like resistors. And everything that you already know about combining resistors in series and parallel also applies to inductors. So in series, we have that the equivalent inductance is the sum of each of the individual inductances. And in parallel, it's just like resistors. L equivalent is 1 over L1 plus 1 over L2, all of them added up, and all of that to the power of minus 1. So just like resistors, that's the way that inductors work. But let's think about capacitors. So if I have capacitors and I connect my capacitors in parallel, so if I do something like this, and I ask, what is the equivalent capacitance of this system? And so here's what my little thought bubble should be. So I have plates, right? Metal plates. So in parallel, I have like bigger plates, right? It's sort of the surface area will combine. Surface area combines. So capacitance is proportional to the surface area of the electrode. So if the surface area is combined, then I have larger capacitance. So the capacitance adds together. Okay, this is the opposite to inductors, and it's the opposite to resistors. So in parallel, our equivalent capacitance is C1 plus C2 plus if there's multiple. So that's C1, C2. These are the different capacitors in my parallel network. And then the one that gets a little bit trickier is if they are in series. And this is not that obvious, but it's the same pattern as the other elements for the parallel case. So it's the same pattern as resistors in parallel. Basically, the equivalent is a 1 over C1 plus a 1 over C2, and we add up as many as there are in parallel, and it is all of that to the power of minus 1. So that's the same pattern as we normally used for parallel combinations for resistors and inductors. But for capacitors, it happens when they are connected in series. So capacitors have the kind of opposite way of combining. Inductors combine like resistors. Capacitors have different rules. So capacitors combine differently. Right, the roles of the series and parallel are swapped. And the way that you can remember it, the way I want you to think about it, is this idea: a capacitor consists of these two plates, and it's all about the surface area. So you've got in parallel, it's kind of the sum of the surface areas, So capacitors in parallel add up, whereas for inductors, it's a coil, and connecting two in series will give you more inductance. So that's kind of the shortcut way to remember which way around these elements actually combine.